Hey everyone, today we're going to talk about the resolution of forces. Basically how we can take a vector and break it up into its component parts. Could be two vectors that made up our resultant. Could be a net force or resultant where we're trying to find the components of the force that are acting in particular directions. So basically, let me change this here. Vectors can be resolved or broken up into what we call component vectors, or the parts that are going to make up a vector. These components are always perpendicular to each other, and basically the components of vector R really are the concurrent forces whose vector sum, if we were to combine those graphically or algebraically, their vector sum is R. So for example, if we had a vector, we'll call that R, the components of that resultant vector, we would call them, we could break it up into what we call a horizontal component. Let's call this B, and a vertical component. We'll call that A. Generally, the perpendicular vector components are given with cardinal directions. So we see them as east-west and north-south. Now we'll look at both an algebraic method and a graphical method of resolving a force or a vector into its component parts. So to do this, let's say we consider vector R, resultant R. First thing we wanted to do, if we wanted to resolve this vector into its component parts, we'd want to construct the horizontal axes to begin drawing the resultant vector. So first thing we do here, and I'll get rid of this for now, so we were considering that vector. First thing we want to do is construct a horizontal x-axis. It's going to give us a starting point. And then we're going to draw the resultant vector. With correct angle and direction. So we consider vector R, we'll call that R, and it's got some angle theta. We can break this up into its components, but first we're going to need to construct the vertical axes. And that's going to be perpendicular to the head resultant vector. So we'll construct our vertical axes. We'll call that Y. Now our component parts here, if we think about the vector work we've been doing, and we had, let's say, vectors on our x and our y, they would combine to form our resultant r. But we can trace this back down to a little dotted line here. And this is essentially the point, or the magnitude of the components of r. We would call this the x component of r sub x, and the y component of r sub y, where the distance from the origin up to our perpendicular component there of our resultant would be the components of r in the x direction and in the y direction. Now this is how we would take a resultant or a single vector and resolve it into its component parts. We could then measure r and y, r of x. The combined effect of those two forces would produce the resultant r up there. The algebraic method is a little bit easier. As long as we know the angle that the vector forms with the horizontal axes, we can use the algebraic method outlined here. If we're looking for the x component of vector A, we can use A cosine theta. If we're looking for the vertical or y component, we can use A sine theta, where A would be the magnitude of the vector, and theta being the angle with which vector A is being acted on. So let's see what this means here. If we consider vector force A in this diagram, A makes angle theta with the horizontal x-axis. We can find the x component, A of x, as A cosine theta, and we can find the y component, A of y, as A sine theta. I'm going to do an example here. Given a resultant vector of 60 meters at 28 degrees north of east, use the dot to begin your diagram. That's missing some things there. We're going to resolve this into its component parts. So the first thing that we're going to want to do is construct the horizontal axes, and that should be horizontal. So we can start drawing the resultant. We know that the vector is 60 meters at 28 degrees north of east. We could say on here, let's say we do 10 meters. We're going to set up a scale here equals 1 centimeter. So I'm going to draw a 6 centimeter line, 28 degrees north of our x-axis. So this angle here is 28 degrees. So we have correct angle and direction. This would be a 60 meter vector, or 6 centimeters. We can construct our perpendicular axes here, our y component. And then we can use, since we're not going to do this graphically, we can use to find our x component, A of x equals A cosine theta. So to find the x component of force A, and again this is force A, we know that that was 60 meters at an angle of 28 degrees. That's our x component. This would get us a value here of 79 meters. So our a of x down here, essentially this value, if we were to trace this and do this graphically, a of x equals 79 meters. And this would be, we want to make sure we include this here. This would be 79 meters east, or in the x direction there. To find the y component, we use a sine theta. So we're still using the same magnitude of a, 60 meters, times the sine of 28 degrees. This gives us a y component of 28 meters north. And graphically this would look like this. We'd have a of y equal to 28 meters. So in reality, and this is not, the x and the y are not equal in magnitude, that's why our angle of 28 degrees is more towards the x there, because the x magnitude is greater than the y. So that resultant might have been the product of something like this, where we got a resultant that was more towards the x-axis because the magnitude of that component was much greater. So that's using the algebraic method to resolve a vector into its component parts. This next one here, I'm going to have you guys complete and turn in the answer for the resultant between vectors a and b, and I'd like you to turn that in for your homework credit. I will stamp your notes, but I'd like to see the magnitude and direction of that resultant to receive full credit for the assignment. So to kind of give you a little idea here, we have to use, with this, we're going to use the triangle method. And after we measure here, angle of 49 degrees, and we translate B over to here, what would our resultant be? And that's what I'd like you to find. Our angle between A and B is 49 degrees, which makes our angle up here 131 degrees. From this point, or even really from the beginning, you should be able to find that resultant. We wouldn't use a graphical or algebraic method to do this, given the angles and the multiple components here. So we'll use the triangle or parallelogram method. The last thing here that we're going to practice, sometimes you'll be asked to find a missing component of a vector, or to find a resultant, or to give a possible vector component or resultant given two vectors. So if we consider vector A and the resultant given there, what would vector B look like in order to form resultant R with vector A? So we know that vectors have to be connected head to tail. And B, wherever it is, we're just going to call this B, wherever we're going to put that has to be connected head to tail with A. We then take, to measure or draw on our resultant, we draw from the originating point, or the tail of A, to the head of B. So basically this line, R, has to get drawn from A to the head of B. We'll consider that the same angle as the R that's listed there. So now to find B, B would have to connect to the head of A across. This would be our B. Make sure we're connected head to tail. Make sure you're drawing these with a ruler. Direction here will matter. So make sure that these are drawn to scale. Leave you with a joke today. What did Donald Duck say in his graduate physics class? Quark, quark, quark. Have a nice day.